more accusations of cover-up. The calibration team moves frame by frame, cross-referencing predicted target motion against actual pixel trails, flagging anomalies for manual review. Every odd flash and candidate fragment is recorded, debated, and either cleared or escalated. Nobody at JPL claims that the delay is pleasant. The reality is a bottleneck of caution, one that puts scientific integrity above speed. The next release will have to satisfy more than just curiosity while the world waits. Whether Mars's cameras captured a single nucleus, a collection of fragments, or something that necessitates a novel explanation, it must settle with evidence. A comet's green glow seen from millions of kilometers away is usually an open and shut case. When sunlight breaks its molecular bonds, dicarbon or C2 releases a bright green signature. This process is so reliable that comet hunters use it as a chemical calling card. In the case of 3 Atlas, the story gets tangled. Reports from the Mars flyby window claim a fleeting green flash captured at 003 UTC in some of the Perseverance frame stacks. The implication is simple. Dicarbon should be present and active in the coma if the flash is real. But Mars Express and TGO's early provisional spectra suggest the opposite. Instead of the expected C2 emission bands, which are weak or even absent, a volatile mixture of carbon dioxide-rich and carbon-depleted classic carbon chains takes their place. In lab terms, a green flash without dicarbon is a contradiction. For a spectrum that glows green but lacks the Swan bands at 516 and 563 nanomi, standard cometary physics has no easy answer. If the color is real, there needs to be a new mechanism or new contaminant in action. Spectroscopists trained to chase down false positives urge caution. The chemical paradox cannot be verified without calibrated time-locked spectra that are linked to the precise moment of the reported flash. Was the green a real emission event or a digital artifact from stacking and color correction? Direct instrument-verified spectra are the only way to resolve the contradiction until the raw Mars orbiter data drop. The next round of releases will need to show pixel by pixel whether 3I-LAS's chemistry can actually break the rules. Spectral data from the Mars campaign lands like a challenge to textbook comet science. Early reports from the Mars Express team highlight an emission fingerprint dominated by nickel, not iron, a reversal of what solar system comets display. Nickel lines, which are typically weak or obscured by iron, now tower over the spectrum. When planetary chemists look at the ratios, they find that none of the common formation models can predict this order of abundance. Metals are only the beginning of the anomaly. Trace gas orbiters' instruments bog a volatile mix where carbon dioxide outgassing dwarfs water vapor by an order of magnitude. Water is supposed to be the driver here for a comet heating up close to the sun. Water is almost non-existent, so carbon dioxide reigns supreme. Jet geometry throws another curve. Even at their core scale, images from the Mars orbiter show a plume that is not trailing away from the sun but rather blasting forward, with a sharply defined anti-tail and sunwood. This jet falls off so steeply that dust models struggle to fit it. The classic broad fan-shaped tail is missing. Instead, the plume's leading edge is crispy, the brightness gradient unnaturally steep. According to dynamic simulation teams, such a plume could only be sustained by a very large and dense nucleus without being blown off course. Tracking teams calculate the object's mass by watching for any non-gravitational acceleration, tiny nudges from jets or uneven outgassing. For 3 Atlas, the answer is silence. Its path almost perfectly hugs the predicted gravitational arc, even with visible activity. The implied lower bound 10 billion tons more asteroid than comet. Every oddity is recorded, discussed, and stacked into a dossier that is growing. In order to explain the chemistry, dynamics, and sheer mass, natural models are stretched. The stakes climb, as the scientific community weighs whether these signatures point to an object that simply rewrites the comet rulebook or something that can't be written off as natural at all. Avi Bay, known for pushing the boundaries of interstellar research, enters the debate with a provocative calculation. His team uses orbital models and back-racing the 3I-LAS path over decades to see if it overlaps with the well-known 1977 WOW signal, a 72-second radio burst at 1,420 MHz known as the hydrogen line. They estimate that there is a 0.6% chance of such a sky position coincidence using Monte Carlo and JPL Horizon simulations. That's rare but not impossible. In SEI circles, the hydrogen line has special significance. It's the frequency most likely to be used for interstellar signaling. According to Lowe's group, any object that moves at interstellar speed and passes through the WOW coordinates merits a targeted radio follow-up. The dangers of post hoc reasoning, positional uncertainty, and the vastness of the sky are all highlighted by SEI researchers, who remain cautious. A narrowband hydrogen line signal specificity is still the gold standard for artificiality. Nature doesn't broadcast in such a tight channel. With 3 Panbai TLAs now behind the sun, the question lingers: will the next radio window reveal anything more than silence? After October 29th, 3I LAS slips behind the sun, entering a blackout zone that blinds both Earth and Mars-based observers. For the next 5 weeks, no telescope can track its position, brightness, or evolving structure. This is not an unusual gap. Perihelion always brings a forced pause dictated by the sun's glare and the hard limits of spacecraft safety protocols. Throughout November, planetary scientists, amateur astronomers, and techno-signature advocates all watch the calendar, waiting for early December when the object will finally reappear in the pre-dawn sky. The watch list is dominated by 4 key metrics: overall brightness, trajectory against background stars, tail or jet morphology, and spectral fingerprints. Each will be scrutinized for changes. Has the object fragmented, faded, or shifted course? The next window is brief but decisive. Verification will depend on what emerges from that solar shadow, and whether the data matches predictions or deepens the mystery. Sorting signal from noise begins with a simple ladder. Reliability is at the foundation. Whether they are companions, flashes, or streaks, genuine features must appear in distinct stacks with timestamps and ephemeris that match across teams. Artifacts, by contrast, vanish when pipelines shift or calibration changes. Next, multiband confirmation. A real object should register in more than one filter or wavelength with color ratios that make physical sense. Under various processing, artifacts frequently flicker in a single channel or change color. Above that, geometric and dynamic hallmarks. True companions should move in parallel, trackable against predicted paths and maintain consistent separation, never jumping or blurring with stack order. The top rung, maneuver or structure, deliberate motion, narrowband radio, or repeating geometry. The natural world can't even come close to making these up. Each claim climbs this ladder, facing harder tests at every step. As the claim grows, so does the burden of proof. The scorecard is open. Mark every anomaly, demand receipts, and let the evidence speak. Chemically 3I Atlas Challenger's Comet models. Its nickel to iron ratio, carbon dioxide heavy composition, and massive sunwood plume all stand out. However, the most crucial evidence is still hidden from view. With a calculated probability of 0.6%, the object's projected path overlaps the location of the 1977 WOW signal, but no independent radio detections have yet emerged. As 3I Atlas approaches perihelion and a blackout in observations, the facts demand patience and rigor. Until the next data release, the mystery stands. We have an interstellar puzzle, a stack of anomalies and no confirmed answers. Only the evidence and what we do with it next.